In this chapter that we're going to be taking a look at in the near future, we're going to be dealing a lot with ratios and proportions. Now, these are things that you should have learned about at some point previous to this, but we need to probably review a few kind of key components to ratios and proportions. Some things that you're going to need to make sure you're familiar with as we move on through this chapter. So first of all, if you need to pause the video to copy down all these notes, you can go ahead and do that now. I'm going to go ahead and explain some of the things that I've got here. First of all, what a ratio is just a comparison of one number to another by division. Or another way to say it is the ratio of one number to another is the result when the first number is divided by the other. And just as a reminder, the answer to a division, the result of division, we call that a quotient, right? So adding, it gives you a sum, subtracting gives you a difference, multiplying gives you a product, dividing gives you a quotient. So the ratio of two numbers is just what you have when you take one number divided by another. Really, that's as simple as it gets. Some things that you need to remember about ratios, we can write them in a number of ways. We can write ratios as fractions, so maybe we have a ratio of A over B. We could use the word 2, so we can say A to B. Or we can use a colon and say A colon B. All of these mean the same thing. They're all equivalent forms. That you might see different ratios written different way, but they all mean the same thing. They should be expressed in simplest form, or as many of us would think of as reduced. So we know that when we see a fraction, we always want to try to reduce fractions, divide the numerator and the denominator by the same thing. We're going to do the same thing with ratios. Even if they're written as colons or written with the word 2, we're still going to try and divide both numbers by the same thing to kind of get that ratio down into simplest form or reduced form. Because we're dividing, we cannot have the denominator, of course, equal to 0 because you're not allowed to divide by 0. That's against the laws of mathematics. So we always remember that that bottom number cannot be 0. A lot of times ratios compare measurements, angle measures or segment lengths, areas, etc. Whenever we're using a ratio to compare two measurements, we probably want the two numbers that are the measurements, we want them to be in the same unit. So both in feet or both in centimeters or both in, if you're talking about time, you maybe want to put them both in minutes or seconds or something like that. We can compare three or more numbers as a ratio, in which case we're probably going to use the colon form of the ratio. The other ones don't make as much sense. So like for instance, if I wanted to compare three numbers A, B, and C, I would just write it as A colon B colon C. That's still considered a ratio. Proportion is something we'll deal a lot with. That's what we get when you take two ratios and set them equal to each other. So if I say A over B is equal to C over D, I have a ratio here of A to B, another ratio of C to D, and I set them equal. That creates what we call a proportion. And we're going to deal more with proportions in the next video. If you want to do three or more ratios, you could just create an extended proportion. So we could tack on an equals E over F. If we could just keep going if we wanted to kind of make an extended proportion where we have more and more ratios that are all said to be equal to each other. So what can we do with this? Well, let's take a look. In this example right here, we have two triangles. And the first thing I want to do is find the ratio of AE to BE. So I'm going to put AE over BE, the length of segment AE divided by the length of segment BE. Well, in this picture, the length of AE is given as 10. The length of BE is given as 5x. Now there's my ratio, but of course, like I said on the previous slide, I want to make this in simplest form. So I'm going to look for something that I can divide both the numerator and the denominator by. And for this example, it's pretty clear. I can divide them both by 5. That's going to leave me 2 in my numerator. 5x divided by 5 will just give me x in my denominator. So 2 over x is my ratio of AE to BE. Part B says find the ratio of the largest angle of triangle ACE to the smallest angle of triangle DBE. Well, let's look here for a second. What are the other angles? Of course, I have a 60-degree angle here at angle A. If I have a 90-degree angle right here, I know that this is also a 90-degree angle. And since this is a right triangle, these two acute angles should add up to 90. They should be complementary. So if this one's 60, that one's going to be 30. Over here, I have my 90-degree angle. I have a 30-degree angle here. So that's going to be a 60-degree angle here. Now, the order in which these things are listed in my ratio is important. The first thing that's listed goes on top of my fraction. So the largest angle of triangle ACE, that's 90. That's going to go on top of my fraction. The smallest angle of triangle DBE, that's 30. So now I want to, again, simplify this. I can divide both the top and the bottom, in this case, by 30, and that'll give me 3 over 1. Now, I know that we're used to seeing a fraction 3 over 1, and we're just going to write it as 3. If we're doing it as a ratio, we don't want to do that. Right? I know the fraction 3 over 1 equals 3. But in this case, I want to have both numbers, the 3 and the 1, because I'm making a ratio. And a ratio compares two numbers. So I'm going to leave my answer as 3 over 1. In the next example, we have a rectangular field that has a length of 1.4 kilometers and a width of 500 meters. And we want to find the ratio of the length to the width. So we're going to have the length over the width. In this problem, it gives the length as 1.4 kilometers and the width as 500 meters. Now, as I said, I want to have, if I'm comparing these two things, I want to have them in the same unit, because when we write our final ratio, we actually don't want to have any units in it. So we want to be able to cancel the units out because they're the same on the top and the bottom. That's another way to think of this. So how can I turn one of these two units into the other one? Well, I could turn meters into kilometers by dividing by 1,000. But that would give me a 1.4 over 0.5, and I probably don't want that. What I might want to do instead is say, well, if I take kilometers and I multiply it by 1,000, what I end up with is a certain number of meters. So 1.4 times 1,000, that's 1,400 meters. You should have learned about this in your science classes, I would think, right? How to convert kilometers to meters and so on in the metric system. So 1.4 kilometers is 1,400 meters. Now I'm over 500 meters, and you can see I have the same unit on the top and the bottom, and those units are going to cancel out. I can also take, because I have two numbers that end in zeros, I can cancel out a 0 and a 0. I essentially just divided by 10 there. I can do it again, divide by 10 again, and now I have 14 over 5. Since 5 is a prime number, it can only be divided by 1 in itself. 14 cannot be divided by 5, so we're going to leave it as 14 over 5. We're not going to turn that into a mixed number, right? We're not going to say 2 4/5, which is what this would equal if I made it into a mixed number. We're going to leave it as an improper fraction, 14 over 5. In this final example here, it says the ratio of the angles of a triangle is 2 to 3 to 5. So we have kind of a ratio of three numbers here. Let's sketch out what this triangle might look like. I have angles. Well, it tells me that the angles are 2, 3, and 5. But I know that that wouldn't be the actual angle measures, right? Because 2 plus 3 plus 5 only adds up to 10. And I know in a triangle, these angles are going to add up to 180. So I start thinking, well, where did this 2, 3, and 5 come from? Well, what I really had is I originally had three numbers for the angle measures, and I divided each one by something. So I took this guy and I divided by some unknown number. And I did the same thing on all of them, right? I divided all three by the same number. And what I came out with was 2, 3, and 5. So the number that was originally here, and originally here, and originally here, was this mystery number, which instead of saying a question mark, let's put an X there to stand for this number that we don't know the value of, right? This number is 2 times X, right? Because if I took this number and divided by X, I ended up with 2. So if I work backwards, 2 times X is what this number is right there. This guy here is 3X, and this guy here is 5X, right? This is the simplified version of the ratio of these angle measures. When I simplified that, I divided them all by the same thing, and I ended up with 2, 3, and 5. So we're going to kind of work backwards there. This is not a 3, it's a 3x. This is not a 2, it's a 2x. This is not a 5, it's a 5x. Now, if I can find that value of x, I can multiply it by 2, by 3, and by 5, and I'd have my angle measures. Well, thankfully, I know that 2x plus 3x plus 5x in this picture should equal 180 because those are the angles of this triangle. So 10x is equal to 180, which means that x must be 18. So my first angle is 2 times 18, which is 36 degrees. My next angle is 3 times 18, which is 54 degrees. And then my last angle is 5 times 18, which is 90 degrees. So my angle measures in this triangle are 36, 54, and 90.